We have some, you want to hand in your problem sets, and we have 3 handouts, the old problem set solutions, the new problem set, and we're also handing out Chapter 8 today. Of course, these are all on the web. Reminders of previously announced events. Next week, I'm going to be away. Ralph Cutter will be a much improved substitute. He'll be talking about Reed-Solomon codes and Reed-Solomon decoding. He's one of the world experts on these things. He's a great lecturer, so you're really lucky, I believe. I will, of course, look at the video afterwards and see how he did, but I'm sure he'll do it better than I would have done it. And midterm is in 2 weeks, and that's just a reminder. When I come back, we'll have a Monday class to go over anything that Ralph may have missed, or really anything in the whole course up through Chapter 8. You can bring questions into that. I don't know, how much I'll feel I need to embellish and cover, so I don't know how much time there'll be for questions, but that can be a fairly free-form lecture. And then Ashish is going to run a review session on the Tuesday with exactly the same purpose. So hopefully that'll put you in good shape for the midterm. And we have to make up a midterm. No idea what's going to be on the midterm yet. Okay, any questions about these things? Homework process is going okay? Office hours? Solutions? Everything seems to be all right so far. Good. Okay, we're in Chapter 7. I certainly plan to complete it today. I'm not going to cover all of Chapter 7, but the key elements that I want you to know, you're responsible only for what's covered in class, by the way. We've talked about a lot of algebraic objects, and at this point we're basically, our main emphasis has been to get to finite fields, and at this point we have prime fields with a prime number p of elements. And we find that we can construct such a field by taking the integers mod p. You can write that as z mod pz. You can equally well consider this as the equivalence classes of integers with of the cosets of pz in z, which are each identified by a remainder or residue r between 0 and p minus 1. Okay, so basically the elements of the field are these remainders or these cosets. There are p of them. We do arithmetic by simply doing mod p addition and multiplication. So if you understand arithmetic mod p, you understand this field. Yes? Excuse me?
That's FP is ZP, isomorphic?
As an additive group, it's isomorphic to ZP. ZP, we use that notation for the group. We use this notation for the field. And I write ZP is isomorphic to Z mod PZ as a quotient group. Here I've added in the multiplication operation mod p to make this a field. So this is somewhat more than just a quotient group. Sorry, these are all, the notation is supposed to be more suggestive than precise. This is not a math class. I hope it's helpful rather than otherwise. Okay, so today we're going to construct all the rest of the finite fields. By the way, we showed that if a field, these are the only fields with a prime number of elements. Today we're going to construct fields with a prime power number of elements in a very analogous way. And it will turn out, although I'm not going to prove this, that these are the only finite fields. They're either, these are generalizations of this, so all finite fields have a prime power number of elements and are basically isomorphic to one of these fields. All right. How do we construct this field? To give you a preview, very analogously to the way we constructed this field. You'll see that the character of the arguments is very much the same, and it's because there's a great algebraic similarity between the integers and the polynomials over a field. And we'll talk about that in a second. But basically, they're both countably infinite rings, or infinite rings, countably infinite if it's over a finite field. And they both have analogous factorization properties. They're both unique factorization domains, would be one characterization algebraically. All right, how do we construct this field? We're basically going to construct it by taking the set of all polynomials over Fp, which is denoted by Fp of square brackets x. And we're going to take that mod, the set of all polynomials that are divisible by g of x, or g of x times the set of all polynomials, the set of all multiples of g of x, or more simply just mod g of x, where we're going to take g of x to be a prime polynomial, and I guess I have to add that the degree of g of x is going to be equal to m. So we basically need to find a prime polynomial of degree m. Then we take the set of all polynomials modulo this prime polynomial. They're going to be exactly p to the m residue classes or equivalence classes or remainders modulo g of x. And we'll use the arithmetic operations from mod g of x arithmetic, addition mod g of x, multiplication mod g of x, and we'll find that the resulting object satisfies the axioms of a field. Okay, so that's where we're going. You with me? Okay, so let's talk about factorization. I think it makes it easy to understand polynomials if we understand the analogies to the integers. In particular, where I'm headed is unique factorization. Both the integers and the polynomials have unique factorizations. The integers into a product of integers, and the polynomial, any polynomial is uniquely factorizable into a product of polynomials. Now, I wasn't quite precise when I said that. We have to be a little bit more precise when we talk about factorization. In particular, we have a certain kind of trivial factorization that involves units. Units, as you remember, are the invertible elements. We're in a ring, so not every element has an inverse, but some of them do. And in the integers, what were the invertible integers under multiplication? Everything here is about multiplication, yeah? A ring is something that satisfies all of the properties of a field, except that some of the elements don't have inverses, so the division is not necessarily well defined, even for non-zero elements. Okay, sorry. I think I said that before, but we're not emphasizing that these are rings, however they are. That's an informal definition. Okay, so in the integers, of course, 12 doesn't have a multiplicative inverse that's an integer. But which integers do have multiplicative inverses? Plus minus 1. So if an integer is divisible by n, it's also divisible by minus n. All right? Trivially. These are the only ones in the integers. And last time we actually talked, if I remember correctly, about the units and the polynomials. Which polynomials have inverses? Excuse me? The degree 0. Thank you. The degree 0 polynomials have inverses because they are basically the non-zero elements of the field. Okay, slight abuse of notation. We identify the field elements with the degree 0 polynomials. These are polynomials just of the form f of x equals f naught, a constant, where the constant is non-zero. Okay, so similarly, we will have to have representatives of equivalence classes with respect to the units. So, if both plus or minus n divide something, what we take as the representative is we take the positive integers. When we talk about divisibility, we talk only about divisibility by positive integers or factorization by positive integers. It's trivial that if something is divisible by n, it's also divisible by minus n. Similarly, for polynomials, the representatives are taken as monic polynomials. And this means that the highest order term, fm, is equal to 1. Okay, so we can take any polynomial, and by multiplying it by one of these invertible elements, basically by a non-zero constant in the ground field, we can make the highest order term equal to 1, right? So if a polynomial is divisible by f of x, it's also divisible by alpha f of x, where alpha is any field element, non-zero field element, right? And so we may as well fix the highest order coefficient equal to 1. Actually, for some purposes in literature, like you've probably seen this in filter design, or we always make the lowest order coefficient equal to 1, f naught equal to 1. You could also adopt that convention and say that that's going to be my monic polynomial. Here we'll focus on the high order coefficient, but you can do it either way. And these both have the nice property that the product of positive integers is a positive integer. Product of monic polynomials is a monic polynomial, right? It's going to be the highest order term of the product is going to have highest order term equal to 1. Or if you chose the lowest order one, that would work too. The lowest order term would be equal to, of the product would be equal to 1. All right, so having recognized this, when we talk about unique factorization, just as with the integers, what we really mean is factorization of a positive integer into a product of positive integers. It's unique up to units. All right, we can always put units either on the integer that we're factoring or on any of the factors, and we can freely multiply any of these things by units, and it won't affect the factorization. Similarly, over here, when we talk about unique factorization, we mean unique up to units. We're basically going to talk about the factorization of monic polynomials into a product of monic polynomials. Okay? I'm not getting a real positive feeling that everybody's following me, but it helped if I wrote down more things or wrote some examples. In f2 of x, for instance, this isn't a very good example. Let's write r of x. Okay? We're going to talk about factorizations like this. X squared minus 1 equals x minus 1 times x plus 1. All right? That's a factorization of a monic polynomial into a product of monic polynomials of lower degree. All right, it happens in f2 of x, since there is only one non-zero field element, that all polynomials are monic except for the zero polynomial. All right, the only non-zero term we have to play with is 1, so the highest order non-zero term is always 1. All right, okay, so that's what we're going to mean by unique factorization. Now, there's one other qualifier there are some trivial factors, or divisors, I guess I should, well, trivial factors. I forget, we took some care to use the standard mathematical terminology in the notes, so if it says trivial divisors, then that's what I mean. What would the trivial divisors of integer n be? Yeah, 1 and n are always going to divide n. And we're really not interested in those when we talk about factorization. All right. All right, similarly over here, the trivial divisors of a polynomial f of x are 1 and f of x. We're not interested in those. Okay, so when we talk about unique factorization, we mean up to units and non-trivial factors. And for the integers, that means that we're going to talk about factors, divisors d, let's say, such that d is between 1 and n. Okay? And for polynomials, what this means is that we're not interested in degree 0 factors. We're not in the only factor of degree the same as f of x is going to be f of x up to units. We're interested in divisors d of x such that the degree that 0 is less than the degree of the divisor less than the degree of what it's dividing into. Sorry, I'm not defining everything, but I hope that's clear. We're just interested in factors that have degree less than the polynomial that we're factoring, but we're not interested in degree 0 factors. All right, so that's what's meant by unique factorization. It also shows you the analogy in general. In the case of integers, the key thing in a divisor is that it have magnitude between 1 and n. The key thing in a polynomial is that it have degree between 0 and the degree of f of x. Basically, we want to factor something into smaller things here. And when we say smaller, we're talking about magnitudes. Here, when we say smaller, we're talking about degrees. In general, when we go between these two things, the concept of magnitude is replaced by the concept of degree to say how big something is. In both of these, the key to all proofs is the Euclidean division algorithm. If you perform the algorithm, then you will find, suppose we want to see if n is a divisor of m. I've forgotten what I put in the notes. Then we go through division, and we find that m is equal to q, some quotient times n, plus a remainder r. All right, this is standard grade school division, but it's really the key to the universe in talking about these two domains. And this is what we've used really to prove everything about the factorization properties of integers. And how would you actually prove that everything can be written this way? There's an important caveat that the remainder we can always choose to be in the range from 0 less than r less than or equal to n minus 1. And the remainder is what we call m mod n. All right. We divide and we get a remainder that's one of these n things, and that tells us that's the main thing we get out of this division is m mod n, which is equal to the remainder r. All right, and there are precisely n remainders. Now, how do you actually prove this? You prove this, if you want, very easily, just by recursion. You take an integer n, you take m, and you ask, is it already in this range? If it is, you're done. M is the remainder, and q is 0. If not, then you subtract n from m, thereby reducing the magnitude of m. You're going to use the magnitude as an indicator of how far you've gotten in this process. You reduce the magnitude, and then you ask, is the result in this range? Okay? If it's in that range, fine, you finish this and q is 1. Otherwise, you continue. And in the recursion, you're continually reducing the magnitude. And it's easy to show that eventually the magnitude has to fall into this range and be one of these n remainder numbers. And then you're done. Okay, so it's a descending chain where the chain has a bottom at 0. You start with a positive integer. You can't go below 0. And this is the only way it can come out. It's very easy to prove that. All right, similarly in polynomials, we get an analogous expression. If we want to take f of x and see if g of x is a divisor, we take f of x, and we can always write this as some quotient times g of x plus some remainder, where the important thing here about the remainder is that the degree of the remainder is less than the degree of g of x. And here the remainder is called f of x mod g of x, just as the remainder here is called m mod n. And the remainder is, there's a unique remainder. And again, how would you prove this? You can just take any long division algorithm that you know for dividing g of x into f of x. Basically, long division amounts to taking f of x. You can always choose some scalar multiple of g of x to such that f of x minus alpha g of x has degree less than f of x. So you pick the top term to reduce the degree. All right? Let's take g of x to be monic. We're only interested in monic polynomials. If the top term of fx is, well, we're only going to divide it into monic polynomials. So, all right, but as we go along, we may get non-monic ones. So you take the top term, whatever it is over here, fm, you multiply fm times g of x, you subtract fm g of x from f of x, you reduce the degree. Okay?
Another x raised to something.
Correct. Thank you very much. You need also a term x to the, whatever the difference in degrees is here, to move the degree up to the top. All right, when we're actually doing long division, we write fm minus 1, down to f naught. We divide g n down to g1, and the first term, gn is going to be equal to 1. We take fm up here. We implicitly move it over to get fm down to fm alpha. We subtract, and we're down to something that only has degree m minus 1. That's what long division, polynomial long division is shorthand for. All right. So you all know how to do this. Okay, again, similar kind of proof that you must be able to get a remainder in this range, and furthermore, the remainder is unique. You basically can go through this process. You reduce the degree by at least 1 every time. Therefore, the degree is must eventually be reduced till where it's less than degree g of x. At that point, you can't continue this process. All right, you're stuck, and that's your remainder. There's no way of taking something of lesser degree of g of x and subtracting some multiple from g of x from it to still further reduce the degree. All right, so similar proof. Uniqueness is pretty obvious. So you get a unique remainder of lesser degree than g of x. Okay, and so you can reduce any f of x to some r of x, to some remainder r of x, which is called f of x mod g of x. Okay, and if we do arithmetic, the way we do arithmetic over here for addition is if we want to add two remainders, mod n, we take the sum of them, and then if necessary, reduce them mod n. Similarly with multiplication. If we want to multiply them, we take the product of two remainders, and if necessary, reduce them again to a legitimate remainder, which is in this range, r mod n. It's the same over here. If we want to multiply, if we want to add two remainders, that's easy enough. We can do that, and we won't increase the degree, so we automatically get something when we add two remainders that satisfies this degree property. We don't have to reduce mod g of x. If we multiply, you do have to check that when you multiply two remainders and reduce, then all you need to do is reduce the mod g of x. And basically the assertion is that r of x, s of x, it's hard to write this without being tautological. R of x, s of x, reduced mod n, mod g of x. This is not worth writing. R of x, s of x, mod g of x. Something like that. It's a total tautology. Forget it. It's said correctly in the notes. I'd rather think of it as residue classes. If we talk about this as a coset, r of f of x plus r of x, and we want to multiply any element of this coset times any element of the coset f of x plus s of x, then the result is just multiplying out symbolically. The polynomials times the polynomials are the polynomials. Any polynomial times a polynomial is a polynomial. Plus r of x, f of x. We could get some multiple of r of x, some polynomial multiple. We could get some polynomial multiple of s of x. Plus r of x, s of x. But this is a polynomial. It's included in here. We don't need to say that again. Similarly here. And so this is equal to f of x. It's equal to the coset f of x plus r of x, s of x. But this is another polynomial that probably has higher degree. This is equal to the coset f of x plus r of x, s of x mod g of x. Okay, so this tells us that to multiply cosets, coset with representative r of x times the coset with representative s of x, we're going to get something in the coset whose representative is r of x, s of x, mod g of x. All right, so this is a sketch of a proof that basically mod g of x commutes with multiplication to multiply r of x times s of x. All right, so Are you?
F of x is not general polynomial that has a factor g of x, right? But we didn't mention that we need it.
Yeah, you're quite correct. What I mean is the cosets of g of x, f of x. So I now understand all the blank looks. Are we better off now? These are cosets of g of. We have a group consisting of the set of all multiples of g of x, which I write as g of x times all the polynomials. The cosets of the group are precisely identified. There's one remainder of degree less than g of x in every coset, so this is the representative of the coset. This is a sketch of a proof that that multiplication basically just amounts to multiplying the remainders. We can identify the representative of the product coset is the product of the representatives modulo g of x. I think I said it correctly for once. Please read the notes if you are still confused, as I can see some of you are. Maybe it would help to do an example. Let's take g of x to be equal to x squared plus x plus 1 in f2 of x. It's a binary polynomial. Then r of x, the remainders are equal to 0, 1. Those are the well, this is degree minus infinity. This is degree 0. They're x or x plus 1. Okay? Those are the possible remainders when I take any polynomial modulo g of x. Divided by g of x, I'm going to get a polynomial in f2 of x of degree less than or equal to 1, and those are all of the polynomials. There are precisely 4 of them of degree less than or equal to 1. All right? So what's the addition table? Addition is pretty easy. Zero plus anything is itself. 0. 1 plus 1 in F2 is simply 0. 1 plus x is 1 plus x. Sorry, x plus 1 as I've written it. And 1 plus x plus 1 is x. X plus 1. X plus x is what? Hello? 0. Thank you. X plus 1. Thank you. X plus 1. X plus 1 is 1 and 0. So that's what the addition table looks like. Actually, you can think of these as being just written as binary pairs, 0, 0, 0, 1, 1, 0, 1, 1, where this pair is basically F1, F0. And then the addition table is precisely the same as the addition table for these binary two-tuples. You just add component-wise the lowest order coefficient, the F1 coefficient. So addition is just like addition in F2 squared, or Z2 squared if you like. Okay, that's actually an additive group. Check it out. It's not Z4, by the way. It's the other abelian group, the other group of size 4. It's sometimes called the Klein 4 group, but it's really just the addition table for the set of all binary two tuples. Okay? Multiplication. One very nice thing about finite fields is you can simply, sorry, this was supposed to be addition, this is supposed to be multiplication. You can simply write out what all the rules are in a finite space. Okay, so what's 0 times anything? Okay, what's 1 times anything? Itself. 1 is the multiplicative identity. But you could formally do this by doing polynomial multiplication. All right, here's an interesting one. What's x times x? Let's do x times x. What is that going to be equal to? X plus 1. How did you do that? We did the modulo. First of all, we write that that's x squared. But then we have to do x squared modulo g of x. X squared plus x plus 1. So we have to go through a little long division process. We have to subtract this out from that, and that gives us x plus 1. All right? So that's the key rule. Whenever we see something of degree 2 or higher, we can always reduce it by subtracting out some multiple of g of x down to something of lower degree. All right, so this is what I've been talking about. So x times x is x plus 1. What's x times x plus 1? Equals what? Good. You can do that in your heads. And what's x plus 1 times x plus 1? Remember, we're doing mod 2 arithmetic in our base field here. So this equals what? X squared plus 1. We reduce that, we get x. Okay, let me check right now. Is this a field? These 4 elements with these rules for addition and multiplication, does that form a field? What do I have to check? Apart from formalities like the distributive law, which follows from the distributive law for polynomials. That's always going to hold under mod x arithmetic. What do I have to check? What are my field axioms? Anybody? Closure under multiplication. That's getting towards a very crisp statement of the. I'm looking for 2 group axioms. One has to do with something we have to check for addition. Something has to do with something we have to check for multiplication. Inverses. Okay, between the 2 of you, I heard the 2 answers that I want. We have to check that this forms an abelian group under addition. So we have to check that the addition table is the addition table of an abelian group. And under multiplication, we have to check that the non-zero elements form an abelian group. So just this part of the table has to form an abelian group, and both these have to have an identity, of course, but the identity in mod x, mod g of x arithmetic is always going to be 0 for addition, and it's always going to be 1 for multiplication. All right, so I check this. is this a group table? Basically, I just have to check whether every row and column is a permutation of the elements, and it is. And 0 acts as 0 should act under as the additive identity. All right. Here, what I have to check is that the non-zero elements, these three, form a group under a abelian group under multiplication. Well, there really is only one group of size 3. It is isomorphic to Z3. If I replaced, let's remember what Z3 looks like under addition. This looks like 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2. It's mod 3. 1 plus 1 is 2. 1 plus 2 is 3, which is 0. 1 plus 2 is 3, which is 0. 2 plus 2 equals 1. So, gee whiz. This is isomorphic to that if I relabel 1 by 0, x by 1, and x plus 1 by 2. That's the only thing it could be. It's the only group table in which every row and column is a permutation of every other. Okay? So, we verified that we now have a finite field with 4 elements. Prime power number of elements. Right? The elements of my field are these 4 remainders, or you can think of them as representatives for their cosets, modulo g of x. The addition rule is multiplication modulo g of x. Addition modulo g of x, and the multiplication rule is multiplication modulo g of x. And it satisfies the field axioms, therefore it's a finite field. All right, I can add, subtract. Addition and subtraction basically looks like addition and subtraction of binary 2 tuples. It's just component-wise. Multiplication is a little bit more mysterious right now, but it works. Let me tell you where we're going to go on multiplication. In this case, I can write x plus 1 in a different way. I note that x plus 1 is equal to x squared. All right? So let me write a little log table over here for multiplication purposes. I'm going to write x, I'm going to call that alpha. And x plus 1 is equal to x squared, or it's alpha squared. What's alpha cubed? Alpha cubed is x times this again. So it's, let me look in the table, x times x plus 1 is equal to 1. So 1 equals alpha to the cube, or I could write that as alpha to the 0. If I multiply by x again, I just cycle. So I'm going to get a cyclic group here. I'm now going to write the multiplication table as follows. 0, I'm going to write the elements of the group as 1, alpha, alpha squared, 0, 1, alpha, alpha squared. Again, 0 times anything is 0. We never have to worry about that. 1 alpha, alpha squared. 1 alpha, alpha squared. Alpha times alpha is alpha squared. Alpha times alpha squared is alpha cubed, but that's equal to 1. Alpha, same here. Alpha squared times alpha squared, what's that? alpha to the fourth, but what is alpha fourth equal to if alpha cubed is equal to 1? All right, this has to be equal to alpha. Point is, because of this relationship here, I can always reduce the exponents modulo 3. I basically got a little multiplicative cyclic group of order 3 that is, as of course, isomorphic to the additive group Z3. So there are two ways I can do multiplication. One is I can do it by this mod g of x way. I can represent things by these two tuples, which basically stand for polynomials of degree 1 or less. And I can multiply two of these by simply going through standard polynomial multiplication over the appropriate field. And then I'll likely get some powers of x squared or higher, and I reduce those to modulo x squared plus x plus 1. That's legitimate, and that gives me this table. Or the other thing I can do is for multiplication, I can have a different representation. This is basically just a log table. Okay? For each, I would have in my little computer, I would have a separate table where I write that this corresponds to 0, 0, 1 corresponds to 1, 1, 0 corresponds to alpha, and 1, 1 corresponds to alpha squared. Or, of course, I would just represent these by their exponents and have some special value for 0. And then all I have to do is add exponents modulo 3 for multiplication. All right, so log of x is 1, log of x plus 1 is 2, log of 1 is 0, and then I just use this for my multiplication operation, or equivalently this, cyclic multiplicative group. And then I go through some inverse log operation to get back to the other representation if I wanted to. And in fact, in finite field arithmetic, this is what's typically done. There's just a little table lookup such that you can go back and forth between this representation, which you use for addition, and this representation, which you use for multiplication. Yeah?
To represent 0 in your log table.
You have to represent it as being special in some way. If, in fact, literally I made log x equal to 1, log x plus 1 equal to 2, log 1 equal to 0, one thing I suggest in the notes, you can make log 0 equal to minus infinity. Then it'll always work. If you ever get if you ever multiply by 0, you'll be adding minus infinity. The result will be minus infinity, so the inverse log is 0. So that's one way you could do it. Or you could do what you do in ordinary real and complex arithmetic. You can just say, have some special routine for multiplication by 0 is always 0. Division by 0 is illegal. All right, put out some error message. All right, so that's how you would actually build a little finite field computer for this finite field. Okay, now I chose this advisedly. Suppose I had chosen g of x equal to x squared plus 1. Okay, I can do mod g of x arithmetic for x squared plus 1. Again, my 4 field elements are going to be the 4 binary polynomials of degree 1 or less. The addition table is going to be exactly the same, so let's just write the multiplication table over here. 0, 1, x, x plus 1, 0, 1, x, x plus 1. 0 times anything is 0 in ordinary polynomial multiplication, and therefore also in mod g of x for any g of x. 1 times anything is itself, no problem there. X plus 1. So what we again have to give a little bit of care to x squared. What's that going to be equal to? 1. And x times x plus 1 is equal to what? X squared plus x is equal to what? Looks like a bit of a problem. X plus 1 times x squared, x plus 1 is equal to x squared plus 1. What's that equal? 0. Yuck. Didn't work. What's the essential problem here? Yeah, this clearly is not a group. It's not even closed under multiplication, because x plus 1 times x plus 1 is equal to 0. The essential problem is that there are two polynomials of degree less than 2 whose product is x squared plus 1. In other words, this is factorizable. Okay, in f2 of x. All right, so whereas x squared plus x plus 1, does that have any factors of degree 1 or less? Any non-trivial factors of degree 1 or less? Well, basically, we proved that it didn't when we wrote down this multiplication table. All right, we tried all products of degree 1 or less polynomials where they're both non-zero, and we never got 0. Okay, so this will work if and only if g of x is irreducible, has no non-trivial factors, is a prime polynomial. These are all equivalent in f2 of x. There's this distinction in other fields that irreducible just means has no non-trivial factors. Prime means is a monic polynomial with no non-trivial factors. So that's why I said back here that the way we're ultimately going to have to construct finite fields is take the polynomials in fp of x, we've been looking at f2 of x, modulo a prime polynomial g of x. Okay? So what we're going to need to find is prime polynomials. Let's see, can I already prove that this is going to work for any prime polynomial? So I'm going to force that g of x be equal to a prime polynomial in fp of x of degree m. All right. For example, x squared plus x plus 1 is a prime polynomial. All right, and I'm going to ask if the remainders mod g of x form a field under mod g of x arithmetic. Okay, let's blow this out a little bit. Again, what our the remainder is going to be of a prime polynomial, or of any polynomial of degree m. So this is basically going to be the polynomials of degree less than m in fp of x. How many of them are there, by the way? Excuse me? P to the m. So the size of this is p to the m. And one of the representations for these polynomials is just to write out f naught, f1, up to fm minus 1. So this is basically looks like the polynomial m tuples, set of f naught, f1, up to f minus 1 for each of these an element of the field. Okay, I can make a one-to-one correspondence between the polynomials of degree less than m and the set of all coefficient m tuples over fp. These are just m tuples over fp. So they're p to the m of them. And now, do they form a finite? So that's a finite set, size p to the m. Does it form a field under mod g of x arithmetic?
We can prove the permutation property as we did for integers.
Excuse me?
We can prove the permutation property as we did for integers.
Correct. And that's a homework problem. All right, so I'm not going to do it in class, but I will sketch here how it's going to be done. But I'm glad that you instantly see that, because again, we just model everything we do on what we did for integers. If you remember how we proved it for integers. First of all, we really need to check two things. Addition, just as we did for this specific example up here, we first have to check that the addition table is that of a abelian group, that the supposed field elements form a abelian group under addition. And we've already observed several times that addition is just basically component-wise addition of these m tuples. So it's just like vector addition. All right. And vector addition, of course, has the group property. So addition is basically just like vector addition. Or I could write, perhaps more precisely, zp over m. It's a distinction without a difference, really. So it's just component-wise addition of the coefficients. All right, that's how we do polynomial addition, and it will give us a remainder that has a degree less than m, so we don't have to ever reduce it modulo g of x. We just simply add component-wise. Okay, so that's easy to verify. The addition table is always going to be okay. So what do we have to prove now? We have to, what am I going to call these? R g of x. The remainders mod g of x. For multiplication, we have to prove that R g of x star, the non-zero polynomials, form an abelian group, which, as I say, it's a homework problem. Let me sketch the proof. It's precisely analogous to the proof that we made for ZP star. We basically have to check closure. If we multiply two non-zero polynomials, do we get another non-zero polynomial? Asking another way, is it possible to multiply two polynomials of degree less than m and get a result which is a multiple of g of x, which is either equal to g of x or a multiple of g of x. And it's, I think, easy to convince yourself that if this has no factors, its only factors are itself and 1, no non-trivial factors, then you can't multiply two lesser degree polynomials and get either g of x, of course, or any multiple of g of x. And it's an exercise for the student to write that proof out. Okay, but it's just exactly analogous to the proof that you can't multiply two integers less than a prime p and get a multiple of p. All right, so use that as a model if you want to in your proof. That, of course, depends on this being prime. If this is factorizable, non-prime, then of course there are going to be two non-trivial factors, two remainders of degree less than m, whose product is equal to g of x itself if it's factorizable. So you can't possibly get closure. All right, so this is why non-prime polynomials don't work, just like non-prime integers don't work when we constructed ZP or FP. All right, exactly analogous reason. All right, second question is, when we go through this multiplication, suppose we take r of x times, let's construct the multiplication table. Let's take a particular row. Let's take r of x times all the non-zero things. Can we possibly get any repeats? Can r of x times s of x equal r of x times t of x? And again, it's easy to convince yourself that that's not possible. If that were possible, then r of x times s of x minus t of x would be equal to 0. And so we're back to where we were before, mod g of x. And this is impossible. We can't, these are both degrees less than m. We can't multiply two things of lower degree together to get a multiple of g of x. So it can't equal 0. That means there can't be any repeats. That means that each row is a permutation of every other row. Similarly for columns, if you want to do that, all you have to actually prove is 1. So every row or column is a permutation of every other one, if we just look at the non-zero polynomials, star. And therefore, this forms an abelian group. Whose identity is always 1. All right? Just as we proved up here. So this depends on irreducibility, or depends on no non-trivial factors of g of x. Okay, and that's all we have to check. All right? So, I claim that by this process, I can, given a prime polynomial in fp of x of degree m, I can construct a finite field with p to the m elements, that the addition and multiplication rules can be taken as mod g of x arithmetic, and they will satisfy the field axioms. So you can now construct a finite field for any prime power p to the m, right? There's actually still a hole in this.
It's prime.
Define prime polynomial, the term, or?
Find a g of x of degree m.
Correct. Is there going to be a prime polynomial of every degree? I don't know. Suppose you wanted to find an irreducible polynomial over, say, f2 of x or f3 of x. of degree 4. Could you do that?
I mean, the number of polynomials of degree 4 and write down all products of lower degrees which give degree 4, and if we show that total number there is less than the total number of degree 4 polynomials.
Beautiful. I mean, that's an excellent suggestion. So the question is, does there exist a prime polynomial in fp of x of every degree? Or of a given degree? And there are various ways of attacking this question. First of all, I'll tell you that the answer is yes. Okay? For every p and every m, there does exist a prime polynomial, which is fortunate. So from that, we conclude there is a finite field with p to the m elements for every prime p and every m greater than or equal to 1. All right? Now, how might we prove that? One is look it up on Google. Okay, you can certainly formulate a question on Google, lead you to a web page that will have a listing of all the prime polynomials of all degrees over any field that you're interested in. All right, so perhaps that will suffice for you. 2, what I'm going to talk about is the sieve method. Three, you could do a bound on the number of polynomials of each degree, n of d, and show that it's greater than or equal to 1, always. And this is done in the notes, section 7.9, I think. Or 4, you can do what Mr. Agarwal has suggested. You can actually do the closed form combinatoric formula, which I haven't done any number theory here. There's a little bit of elementary number theory in the notes, Euler numbers, this sort of thing. We get formulas for the number of integers of degree d that, well, there's a number of integers that have multiplicative order d mod n and so forth. This is a lovely combinatoric field. There is a lovely closed form for this that you get from the Möbius inversion formula and can be found in combinatoric books. I know it's in Berlecamp's algebraic coding theory book, and it's extremely pretty. And then, of course, given the formula, you have to prove that all of the, again, n of d is greater than or equal to 1, but there is a closed form expression for it that's you get out of combinatorics. We're not going to do that here. I'll be satisfied. Well, this is the real engineering solution here. This is the mathematical engineering solution. And what do I mean by this, the sieve method? Again, take the analogy with the integers. One of the first mathematical accomplishments was Eratosthenes' sieve for finding prime numbers. How does it work? You start to write down all the, well, imagine first writing down all the integers. All right, cross off 1, start with 2. All right, So the first prime is 2. Now you cross off all multiples of 2. 4, 6, 8, so forth. Okay? So what's the next number that you haven't crossed off? It's 3. So that's the next prime. You cross off all the multiples of 3. 3, 9, so forth. 15. And thereby you continue. So the steps are find the next integer on the list. That's going to be a prime because it won't have been crossed off by any previous steps. It's not a multiple of any integer of lower degree. Then cross off all of its multiples up to however long your scribe has written this on the tablet. And this way you can find the primes up to any number you want. It gets kind of tedious after a while, but you can certainly find all the primes up to 100 in a few minutes doing this, right? Well, it's the same for integers. Same for polynomials. So let's, for instance, do a polynomial sieve. Of course, what we're most interested in is the polynomials with binary coefficients, f2 of x. And how do we do it? Let's write down, let's forget about 0 and 1. Those are not considered to be primes. Let's start with the degree 1 polynomials. What are the degree 1 polynomials? They're x plus 1. Are these factorizable? Obviously, they have their only factors are 1 in themselves. They have no non-trivial factors. So these are primes. Okay. So now let's write down all the polynomials of degree 2. I'm sort of doing this in an interleaved manner. There are going to be 2 of degree 1, 4 of degree 2. All I'm going to do is, well, the only polynomials are monic in f2 of x, so I don't have to make that qualification. All right, so here are the 4 of degree 2, right? Now, I go through with my sieve, and we take out all multiples of x. Multiples of x are polynomials with 0 constant term, right? Lowest order term. So obviously this is a multiple of x, this is a multiple of x. Multiples of x plus 1, how do you recognize those over the binary field? This is basically the polynomial whose root is 1. That means the mod 2 sum of the coefficients is equal to 0. So any polynomial that has an even number of non-zero coefficients is divisible by x plus 1. Did you all get that? If not, try that at home. All right. That's the easy way to recognize whether something is a multiple of x plus 1. It has an even number of non-zero coefficients. All right. So this is a multiple of x plus 1. We wrote it out explicitly. It's x plus 1 squared in f2 of x. And this is not. So there is only one polynomial of degree 2. There's only one prime polynomial over f2 of x of degree 2. So this is our only possible choice if we want to construct a finite field with 4 elements, 2 to the 2 elements. Okay, so that might begin to get us scared. Is it possible that there are no prime polynomials of degree 3? We had 2 here, 1 here. Is it going down? Let's write down the polynomials of degree 3. X third plus 1, x to the 3 plus x to the 3 plus x plus 1, x to the 3 plus x squared, x to the 3 plus x squared plus 1, x to the 3 plus x squared plus x, x to the 3 plus x squared plus x plus 1. 8 of them. So that's working in our favor. We have double the number of polynomials as we go up 1 in degree. And again, let's go through the sieve. Which are multiples of x? Non-zero constant term. Which are multiples of x plus 1? Even number of non-zero coefficients. If you doubt that, write it out. Which are multiples of x squared plus x plus 1? Well, they're going to have to be x squared plus x plus 1 times x plus 1 or times x. So we've already got them. If we take this times itself, we're going to get a polynomial of degree 4. Not going to be in this list. So we have to multiply this by these. We've already got those. So, we found 2. We could use either of these to construct a finite field with 8 elements. Okay? And so forth. And it turns out as you go up to higher degrees that the number now increases very nicely, and there's no problem finding a prime polynomial of each degree. And in fact, you can be cute about it and try to find one with only 3 non-zero terms, or has some other nice property that makes it easy to calculate with, or and so forth. So, do you understand the sieve method? If you do, then I believe you could find suppose you want to construct a field with 64 elements. What do you need? 64 is 2 to the 6th, so you're going to need a polynomial with p equals 2 and m equals 6. You're going to need a binary polynomial of degree 6 that is prime, irreducible. And again, in a few minutes, by going through the sieve process, you can quickly find one, or you can look it up in Google or in Peterson's book or any algebraic coding theory book, or probably a lot of other places. All right, so this is a practical solution for the problem for any given p and m. Of course, it hardly proves that there's one of every degree, because there are kind of an infinite number of degrees. Yeah?
So there's 2 ordered 3 polynomials that are prime. Do those generate 2 separate fields, or are they going to be isomorphic to each other?
Great question. All fields with p to the m elements are isomorphic to each other. All right, that's proved in the notes. I'm not going to do it in class. And the other thing that's proved in the notes is the analog to ZP. There are no other finite fields with other than p to the m number of elements. Okay, so this is it. Now, if you explicitly write out these two and write out their, well, the addition tables are always going to look the same, because it's always just binary 3 tuples in this case, but multiplication tables are going to look different. But there is some isomorphism. X in one may be equivalent to x squared plus 1 on the other one, or something. But if you go through that isomorphism, you'll find that the field tables are the same. Actually, I guess I'm going to prove that, because I'm going to prove that the multiplication table is always cyclic, that the group to which it's isomorphic is Z mod p to the m minus 1, just as it was to Z3 here. And I guess that's sufficient with the addition table isomorphism. Yeah, I guess you have to prove they're equivalent. It's done in a different way in the notes. But you're going to see that all the multiplication group is always a cyclic group with p to the m minus 1 elements. And that goes a long way towards suggesting that these are always going to be isomorphic to each other. Yeah?
Roots, right?
Identify roots? That's, if I understand what you're saying, that's basically the way it's done in the notes. You take, You first show that there's always going to be some primitive element that generates the cyclic group, some single generator such that alpha squared, so forth, is the entire non-zero set. You're going to show that alpha has some minimal polynomial, and the set of all linear combinations of powers of alpha is basically equal to the whole field. And so this allows you to establish the isomorphism. I think that's what you're suggesting. So you're well equipped to read the notes, but I'm not going to do that in class. Yeah, I'm very interested in your questions. Please ask more and as many questions as you like. What I'm getting from it is, you all come from different backgrounds. Some of you have seen this in perhaps a math context or in some other context, or you've seen parts of it, or some of the words are familiar. And of course, there are many different ways to present this and to make the proofs and so forth. So, I'm trying to pick a line that works for the particular results that I want to get to. I don't think you would do anything much different if you wanted to develop finite fields. But the class has a very different set of backgrounds, and I'm trying to reach all of you. Don't be alarmed if you've never seen anything like this before. You're not way behind everybody else either. I think it's pretty easy to understand. Maybe it take you a couple hours longer than somebody who has more background, but not more than that. Okay, so that's how we construct finite fields. You have an example of it. Goodness, is it really 11 o'clock? Okay, so I've simply asserted but not proved. You saw in this case that the multiplicative group was a cyclic group. And we could always, for multiplication, represent group elements by this log table. So I had hoped to prove that in class. I'm not going to be able to prove that in class. And I'll simply ask you to read that too. This is important for working with finite fields because it is the way, probably the preferred way to implement multiplication. So you ought to be thinking of how you would program up, finite field multiplier. One way is polynomial multiplication. The other way is just use the fact that the multiplicative group is cyclic, and then it's easy. Just add exponents and reduce modulo q minus 1. Okay, I'm sorry not to have had a chance to go over that. Next time, Ralph Cutter will start to get into Chapter 8 and read Solomon codes.